Thanks. Okay, so I think I'll just, is this on? Okay, I'm going to get started. So today, well, the last day, we're just going to finish streaming. And I'll just call today the power of random signs. So we're going to see L2 norm estimation. We're going to see fast regression. Point query. Dimensionality reduction. So it might seem like many things. Some of the things actually, all these topics I covered in depth. I do cover in depth in Algorithms for Big Data, CS229R. So I'm not going to provide all proofs here, but I wanted to give you a taste of some of this stuff. Okay. So remember last time, we had a vector x, which was an Rn, and is huge, right? And we wanted to compute functions of x while x is updated in a stream without actually remembering the entire vector x. So receive updates. Xi goes to xi plus v. In a stream. And we must answer queries to f of x. Okay. So last time I said that v was always 1. And it starts off, I should say x starts as a 0 vector. So last time I said v is always 1. Let's say the query we want to answer is the support size of x. That was the distinct elements problem. I showed you that there's some non-trivial algorithm if you assume some idealized hash function. Okay. So good. So what's a different, but there are other functions that you might want to compute, other types of queries. So another f is f of x equals, say, the L2 norm squared of x, or just say the L2 norm. If you can compute this up to some 1 plus epsilon error, you can compute the L2 norm up to some 1 plus roughly epsilon error just by taking the square root at the end. Okay. And the algorithm I'm going to show you is due to Alon, Matthias, and Segi. Okay, so just like with support size, you can't get little o of n space unless you settle for both randomization and approximation. So you're not going to output the true answer. You're going to output the answer up to 1 plus epsilon, let's say up to 1% error, and it's going to be a randomized algorithm that fails with probability 1% or something, unless you allow for both randomization and approximation. Okay, and the AMS algorithm introduces an idea that gets used all over the place in streaming algorithms. And it's particularly important when V can be not only positive but also negative. Okay. So if you think about the algorithm we saw last time where V was always 1, in other words, V was always positive, you couldn't support deletions in the stream, right? So the number of distinct elements is support size. If I later wanted to delete an element that I saw, well, I'm only storing the minimum hash value I ever saw. So if the item corresponding to that minimum hash value gets deleted, then my minimum hash value I'm storing is irrelevant now. And I don't know the second minimum because I didn't store that. So what can my algorithm do? Okay, so linear sketching, what I'm going to show you, allows you to design streaming algorithms that support deletions. So linear sketching. Okay, so it lets you support deletions. And in fact, if you have to support deletions, it's known that essentially any algorithm can be converted into a linear sketch with at most a small blow up in space complexity, like a log n blow up in space. For any query f. With a minor space blow up. If you want to see the details of that, that's due to Lee, Gwynn, and Woodruff. Okay, so let's go back to the problem I stated. So back to f of x being the L2 norm squared. So okay, so what is a linear sketch? I didn't actually. You can if you want. You can. Maybe I'll tell you now what the idea is. So the idea is you pick some matrix. Let's call it pi, which is m by n, and you store y equals pi x in memory. Okay, so initially, let's say y is 0, right? Because pi is 0 is 0. And if pi looks like this, so pi is some fat short matrix. Let's say the columns are pi 1 up to pi n. And let's say it's m-dimensional. It has m rows. If I see an update where I add v to xi, what does that imply I have to do for my streaming algorithm? That implies that y should be incremented as follows. Y should become y plus v times pi I. Right? So I can support arbitrary updates in the stream just by updating my linear sketch like this. And this holds whether I have deletions or insertions. So what's the linear sketch going to be for RF? we'll pick pi ij to be plus minus 1 over root m uniform. Okay, so let's say it has independent entries, and each one is a random sign over root m. And now we have to estimate f of x based on the y we have in memory, right? So we'll estimate the L2 norm squared as just the L2 norm squared of y. Right here. Okay. And let me just, I want to call this random sign sigma ij from now on, just when I get into the analysis. Okay, so why does this work? So the way that many algorithms get analyzed in streaming, including this one, is to first, basically bound the expectation, bound the variance, and then use Chebyshev's inequality. Okay, so let me show you that. So the expectation of y, L2 norm squared, that's equal to, so here's my analysis. Well, actually, before I say that, what do I want to say? I want to say, look, the probability that y L2 norm squared minus x L2 norm squared, what's the probability that this thing deviates by more than epsilon times what it should be? I want to say this is small. I want to say that it's at most a third or something, or 100th. My probability of failure is at most 1%. And by the way, what does this say? This is the same thing as saying that y L2 norm squared, right, is 1 plus or minus epsilon x L2 norm squared, which is what I want. I want to get the answer up to this 1 plus epsilon error. Okay. Is it clear what I mean by this notation? I mean that it's at most 1 plus epsilon times this, and it's at least 1 minus epsilon times this. Well, this thing, this thing is at most the expectation of y L2 norm squared minus the expectation of minus x L2 norm squared over epsilon squared times L2 norm to the fourth. This is Chebyshev's inequality. Right. Yeah. Which is just Markov after you square things. So we just need to understand this expression up top. So first of all, I want to say that this L2 norm of x squared is just the expectation of that. Right, so the expectation of y L2 norm squared, so that's the sum over I. Let's say r from 1 to m, expectation of yi squared, yr squared. That's just linearity of expectation. So I want to understand, what is this quantity here for any fixed r? They're all the same for all r. So what is yr? Yr is just 1 over root m. Oh, did I? Yeah. Right, what is my definition of pi ij? It's this, right? So yr is 1 over root m. sum I from 1 to n of sigma Ri xi. Which implies that yr squared is 1 over m, sum over I from 1 to n, sigma Ri squared xi squared, plus sum of I not equal to j, sigma Ri, sigma Rj, xi xj. So this implies that, and this thing here is just 1. So this implies that the expectation of yr squared is 1 over m L to the norm of x squared plus sum I not equal to j, expectation sigma Ri, sigma Rj, xi xj. But if these things are independent, this is equal to expectation of sigma Ri, expectation of sigma Rj, which is just 0. Right? So this thing goes away. Okay. So this implies that expectation of yr squared is 1 over m times L to the norm squared of x, which implies that expectation of y squared, which we said was 1 over m, which was, sum over r, expectation yr squared is just L to the norm of x squared. Okay. So we know that this thing here is just equal to now the variance of this random variable over epsilon squared times x2 to the 4th. Right. We just showed that that thing is the expectation. So that is the definition of variance. And if this matrix, if the entries of pi really are independent, then that means that the entries of y are independent, right? So now let me say what I want to say. So the variance of this thing is the variance of the sum over r from 1 to m of yr squared. But if you have random variables that are independent of each other, then the variances just add. So this is equal to sum r from 1 to m of the variance of yr squared. So let's bound this thing. So the variance of yr squared, by definition, is what? It's the expectation of yr to the 4th minus the expectation of yr squared squared. And we just said this thing is x L2 norm to the 4th. How about this thing? And there's a 1 over m squared here, I guess. Right? Yeah, so I just squared this thing. So how about this? Well, that we can expand out. So what's yr to the 4th? We wrote what yr is, so that's that's 1 over m squared times a sum I equals 1 to n sigma ri xi to the 4th. Okay. So we want the expectation of this thing. So you could imagine expanding this thing out to the 4th and having lots of monomials, roughly end of the 4th monomials, or exactly end of the 4th monomials. And then you can use linearity of expectation to push this expectation inside. Okay, so some of the terms, so what are you going to have? You can have some terms which are like sigma ri for some I to the 4th power. Okay, or you can have two different indices I and j, and you can have sigma ri squared and sigma rj squared. You can have sigma ri cubed and sigma rj to the 1st power. Basically, these powers have to add up to 4. Right? So let me just write this explicitly. So this is 1 over m squared, and then expectation of sum over I, sigma ri to the 4th, xi to the 4th, plus sum over I not equal to j, sigma ri squared, sigma rj squared, xi squared, xj squared, plus sum I not equal to j, sigma ri cubed, sigma rj, xi cubed, xj, etc. Right? You can also have 3 different indices. 2 of them get raised to the 1st power, 1 gets squared. You get lots of different things going on. Okay, now, when you push this expectation inside, let's look at, for example, this monomial here. I should be clear, there are more things here that I didn't write. Well, first of all, these 2 things are independent of each other. So the expectation of their product is the product of their expectations. And the expectation of a sign to an odd power is 0. So whenever you have any odd powers, the terms just disappear. So this is similar to, I think, way back I had you prove the Chernoff bound using, well, by explicitly writing down all the monomials. Right, so it was the same thing there, that things with odd powers disappeared. So the same thing happens here. And basically the only things you're left with are terms like this and terms like this. Everything else doesn't matter. Okay, so this thing I claim is just 1 over m squared times, you have this term, sum over I xi to the 4th, plus you have the other term, sum I not equal to j, xi squared, xj squared. Okay, so conveniently, is that xi squared? Right. So this thing here is at most sum over I xi squared squared, which is equal to x2 to the 4th. So when you subtract out this thing, right, you're subtracting this out, the overall thing is negative. Should I be a little bit more careful? Right. Oh, yes, good. There's a constant here, which I completely didn't write. Okay, good. I was like, this is a little too good. Yeah, I think it's, because I wrote I not equal to j, I think it's 3. But whatever, there's some constant here. It's not so important. But, okay, so now overall this implies what? What do we have? That the variance of yr squared. Oh, and actually, if I can even be a little more, I can optimize things a little bit more. Let me not do this. Let me just keep it like this. And let me say this is equal to 1 over m squared. This is a constant factor, it doesn't really matter. X2 to the 4th, or at most, no, equal, plus 2 sum I not equal to j, xi squared, xj squared. Right, when you take one of these and add this in, you get exactly this. And then you have this here. OK, great. And then now, conveniently, this thing cancels that. So the variance of yr squared is at most 2 times the sum over I xi squared squared, which is, and there's a division by m squared, which is 2 over m squared times x2 to the 4th. So,
Is there an
expectation? Oh, so, right, so I said that the expectation basically kills all the terms with odd powers. And then terms with even powers, a random sign squared is just 1. So the randomness disappears. So what we just showed is that, well, the variance is the sum of all of those. So the variance is at most 2 over m times x2 to the 4th. I'm sorry? But I summed it m times. Yeah. OK. And we said that the probability that we failed, that was what I just erased here, the probability that we failed was at most this quantity, which was this. So this is at most 2 over m times x2 to the 4th. This is the variance. Times 1 over epsilon squared times x2 to the 4th. Right, so this thing is gone. So if we want this to be less than, say, a third, we'll set m to be something like 6 over epsilon squared, so that this is less than a third. Okay. I'm sorry? There's an m squared. Where? But it's the variance of this, right? Which is that. Yeah. Okay. Okay, great. So in conclusion, oh, you're scribing, right? Is it? Okay, great. If we use like 1 over epsilon squared words of space, our estimate is 1 plus or minus epsilon times L2 norm squared with probability at least 2/3. One thing you can do to amplify this is just repeat this same, basically, let me, to get with probability at least 1 minus delta, what you can do is a common trick. Basically, your linear sketch will be the concatenation of many independent copies of this linear sketch. So you'll have pi up here, which has 1 over epsilon, the 6 over epsilon squared rows. And then you'll have another pi prime down here, which has 6 over epsilon squared rows. Okay. And you'll have, k being something like log 1 over delta independent copies of pi. So it implies you will obtain k independent trials, let's call them y1 up to yk. And the algorithm will estimate yk, or will estimate x L2 norm squared as the median of all these things. Okay. Why does that work? Well, the point is, each one we know works with probability 2/3. And for the median to fail, strictly more than half of them have to fail, right? But we know that basically the expected number that work for us, that give us a good estimate, is k times 2/3. And we fail with this procedure if the number that work is less than k over 2. So there has to be a significant deviation from the expectation in terms of the number of trials that worked. And by a turnoff bound, the probability that we get that kind of deviation decays exponentially in k. And exponentially in k means like 1 over exponential in k is delta, basically. Okay. So expected number of trials succeeding is at least 2/3 of them. We fail if less than k over 2 succeed. Probability that less than k over 2 succeed is exponentially small in k. This is turnoff bound. Okay. Okay, great. Now, so great. So we know that implies space, let's say, 1 over epsilon squared log 1 over delta for a success probability 1 minus delta. And it turns out that this is optimal. So, I mean, there was quite a long line of work showing that this was optimal. I mean, initially, people could get the 1 over epsilon squared, but they couldn't get the product. Well, even before that, people could get 1 over epsilon, but not 1 over epsilon squared. There's quite a chain of papers. I'll just cite the most recent, which finally gets this, which is due to JRAM. Woodruff. This is transactions and algorithms. Well, that's the journal version anyway. Okay, great. So there are many things that I wanted to show you. That was L2 norm estimation. One thing I wanted to say is, so I guess here you already basically see it from the proof, but you're trying to get a low memory algorithm, and this matrix pi, the number of columns of pi is n, right? So if you actually were to store this pi, you'd use more space than storing x by itself, right? Which you don't want to do. So what do? Well, you look at the proof and you say, look, when I needed to calculate the variance and I need to calculate the expectation. When I did those things, here, I need to calculate the expectation of this thing and then the expectation of this whole thing. Okay. If you expand this thing out, you get at most kind of degree 4 polynomials in these random signs, right? And we only needed to be able to say that the products of those 4 things behaved independently, right? Those 4 things were independent. So we just need 4 independent random signs. And we saw earlier in the course that you can generate 4 independent random signs using kind of log n bits, a hash function specified by only log n bits, a 4 independent family. Okay? So this entire matrix pi really, well, each one of these things stacked only needs 4 independence. There are log 1 over delta of them. So the total space is log 1 over delta times log n. Okay. So this whole matrix, this entire thing here is specified using very little space. So log n bits is like a word. So each hash function for each one of these only needs a constant number of words of space. And there are log 1 over delta hash functions because you're repeating this log 1 over delta times. So log 1 over delta words. Okay, so that's really, I'm not hiding anything. That's really the entire analysis of this. Okay. Actually, maybe I'll, before I move to the next board, let me just say one thing. Space is, the space is this, but how about the update time? Right? I said that streaming algorithms are basically small space data structures. In data structures, we care about space, update time, and query time, right? In dynamic data structures. So what's the, ignoring the time to evaluate the hash functions, which is constant anyway with the right hash functions, what is the update time in this algorithm? If you see a new update in the stream, how much time does it take to update your sketch? I guess the hint really should be, right? When you see an update, this is what you have to do. You have to add this into your sketch. Order m, right? Which is this. So the update time is also 1 over epsilon squared log 1 over delta. And the reason for that is that when you're adding in some multiple of a column of this matrix, this is a completely dense matrix, right? Every single entry in this matrix is some random sign. So you have to touch every entry in Y to perform an update. So one way of improving that is to make this thing sparse. And in fact, you can do that. So Thorup and Zhang let me not say the journal version because I might get the year wrong, but the conference version is SOTA 04. They just look at pi being as follows. This is again theta 1 over epsilon squared. You have n columns. And what's your matrix? In each column, you pick a random location, and you put a random sign there, and the rest of that column is 0. And each column looks like this. Your other column, you have a random location, you put a random sign there, everything else is 0. The rest of their algorithm is the same. You maintain y equals pi x, and your estimate of the L2 norm squared of x is just the L2 norm squared of y. Okay? And you basically can show the same exact thing. You can show that the expectation, I'm not going to do it on the board, the expectation of y squared is still x squared. And the variance of y squared, you can show, is still O of 1 over m times x2 to the fourth. Okay, that's a computation, not very different from the computation you saw, which implies that you can use this sketch instead. Okay?
Is there any reason to ever use the dense one?
No. Yeah, so this is just strictly better. And you can do the same thing where you repeat this log 1 over delta times, take the median. So this has update time. What's the update time for this if you want success probability 1 minus delta? Huh? Yeah, log 1 over delta. Okay. Good. So you get rid of this 1 epsilon squared in the update time. And it's actually an open problem that I myself am quite interested in as to whether or not you can do better than this. Okay. Is there an algorithm that achieves success probability 1 minus delta for L2 norm estimation, which gets the right space and gets update time, which is, say, constant? Why not? Or, root log 1 over delta, something. So we can show something. We can show that if you use a linear sketch, the update time has to be roughly root log 1 over delta. Okay. But there's still room, there's a gap there between root log 1 over delta and log 1 over delta. Okay. So that's L2 norm estimation. Okay. Questions about it? Okay. So you might ask, motivations of this thing. Where does it get used? So for example, I can tell you where Thorpe and Zhang were using this thing. So both of them were at AT&T Research, which AT&T has lots of routers, and again, their vector x. N is the number of destination IP addresses, and xi. They didn't even care about deletions. Xi is just how many packets did that destination receive over some time window. And the thing about the L2 norm squared is that it measures kind of spikes, right? Like the thing that measures spikes the most is the infinity norm. Right, in terms of, is there an entry I such that xi is very large, right? You really want the infinity norm, and that will tell you what's the largest xi. It turns out that, unfortunately, there is no space-efficient streaming algorithm for the infinity norm. But the largest value of p, for which there is a space-efficient algorithm for the LP norm, is p being 2. Okay. I'm not going to justify that, but it's known. People have proven that. So they were looking at that to basically estimate skewness in the distribution of packets going to various places as part of a system for detecting denial of service attacks. And they really cared about a faster algorithm because this thing was sitting on the router, right? And network speeds are really fast. They can't afford to spend, let's say you want 1% error on your estimate. So 1 over epsilon squared is 100 squared, which is 10,000. So basically, they just got rid of a factor of 10,000 in their running time, okay, which was very important for them. Okay, so good. So that's L2 norm estimation. It gets used in other places as well. One thing I can mention is you saw on one of your P sets Jacquard similarity, where you wanted to estimate the similarity of two sets, and you used the min of a hash function to do it. Another way of estimating similarity of say, documents, I think in the P set I mentioned the history with like web pages, estimating similarity of web pages, right? Another thing you can do to estimate similarity of web pages is cosine similarity. So for example, xi is number of occurrences of word I in document X. And you normalize the document. Wait, so it's normalized. And what I mean normalized, I mean once you define this vector x, you normalize it so that it has unit norm. So then now you have a bunch of documents, right? So x lies on a circle. You have one document x. You have some other document y. You have another document z, etc. How do you estimate the similarity of two documents using cosine similarity? Well, it basically comes down to the angle between the two documents. If the angle is small, you say the documents are similar. And how can you use this kind of streaming algorithm to estimate cosine similarity? Well, forget about streaming. Just think of it as a method of compressing the document. Instead of storing the document x, you'll store the compression pi x. Okay, this compression is often called a sketch of x. And you really want xy, which is, say, cosine of theta. So you want to know some information about it, right? Cosine of theta is large if theta is small, right? It's 1 if theta is 0. You really want to know this dot product. And what you'll do is you'll estimate as pi x dot pi y, okay? Where pi is exactly the same pi. Okay? And you can do an expectation variance analysis to basically say that this works. It'll give you an additive S epsilon with probability 1 minus delta to the true dot product by redoing this. Or you can just say, look, you can say pi of x minus y squared. No, actually, let me just write it like this. A minus b squared is a squared plus b squared minus 2a dot b. Right? That's just an identity, which implies that a dot b is equal to a squared plus b squared minus a minus b squared over 2. Right? And what do we know about pi? We know pi preserves L2 norm squareds of vectors. Right? So imagine that a is now pi x and b is pi y. We want to understand, what does pi x dot pi y look like? Well, it's pi x L2 norm squared, which is roughly x L2 norm squared, plus pi y L2 norm squared, which is roughly y L2 norm squared, plus pi of this vector. It's some other vector. But pi preserves norms of vectors, so it's roughly what it should be, up to this epsilon error. Right? So the fact that you preserve L2 norms of vectors means you preserve dot products, which means you roughly preserve cosines of angles. So you can use this same exact setup to do cosine similarity. Right? Does that make sense? Okay, so let me show you some more power of random signs. Another example. So let's say statistics, such as linear regression. Right. So the idea here is there's some parameter vector x in RD, and given variables a1 up to 80, our system is linear, and we should have that b is sum of I equals 1 to d of ai xi. So there's some other variable in our system b, and it behaves as a linear function of other variables ai. Okay? And the coefficients of that linear function are these xi's. And we're imagining we don't know the xi's. So we're doing experiments. And based on our experiments, we know a lot of ai's. We know the resulting b. We can observe all these variables. But there are some hidden variables xi that we don't know. And we want to solve for them. And the way this is done is you write a matrix A, which is really, I just think of it as tall and skinny. A1, A2, AN. So it's an n by d matrix. And you want to find x such that, so let me call this b1, such that ax is b, where b is also this n-dimensional vector. Now, usually when you do linear regression statistics, just a show of hands, how many people have heard of linear regression? Okay. So usually you assume that you don't actually observe the true variable, but you observe the variable plus noise. So we observe b, which is a sum of I plus or 1 to d, aixi, plus noise. Noise in our experiment, or there's some noise that's generated as we do this. So we want to find x such that ax is approximately b. Okay, so to be specific, we want to compute x star. Oh yeah, you had a homework on this as well, right? So you want to compute x star, which is the argmin of ax minus b. So yeah, I guess everyone should have heard of least squares regression, unless you dropped that p set. So okay, good. And as we, I guess, almost saw in the p set, you can write that x star is equal to A transpose A pseudo inverse A transpose B. So in the p set, I think I said that A has full column rank, in which case the pseudo inverse is the inverse. I don't want to get into, this is the pseudo inverse. Basically, it's some generalization that also lets you handle the case when it's not full rank. You can go look it up if you want. It's not going to be important for what I say. The thing that is important is, how long does it take to compute A transpose A? N squared, right? Oh, n squared, not n squared. So A is n by d. N times d squared, actually, right? So if you look at A transpose A is a d by n matrix times an n by d matrix, right? So you have to keep doing these dot products like this, okay? Right? Every time you want to compute an entry, so the resulting matrix should be d by d, right? So for each one of these entries, you have to take one of the rows here and a column here and take a dot product. So that's n time, and there are d squared entries. So this implies n times d squared time. And that turns out to be the bottleneck. The pseudo-inverse takes poly d time, like roughly d cubed time. So the bottleneck really is doing A transpose A. I mean, another way of solving, as you saw in the p-set, another way of solving this thing is using gradient descent. You start off with a decent solution, and then you keep refining it using gradient descent. Okay, but let me stick to this for a second. So can we speed this nd squared up using this Thorup-Jong or using the AMS sketch, this random sign sketch? Yes, we can. So let me make a definition. So Sarlosh he says that pi is an epsilon subspace embedding for a subspace V, a linear subspace, if for all vectors v in capital V, we have that pi v L2 norm squared is 1 plus or minus epsilon L2 norm squared. Okay? Okay. So it's sort of like, what we were talking about, preserving L2 norm squareds of vectors, but there are like infinitely many vectors here. Okay. So claim if pi is an epsilon subspace embedding for which subspace? The span of B as well as the columns of A, then if you look at x tilde star, which is the argmin of pi ax minus pi b, it satisfies that ax tilde star minus b is at most 1 plus epsilon over 1 minus epsilon ax star minus b. All right, so ax star minus b is the best you can possibly do. And what I'm saying is, if instead you use this as a substitute for the true optimal vector for regression, you'll do almost as well. And what's the benefit of this? What's the algorithmic benefit of this? So I should say here, hopefully, m is much less than n. Right, so this is an m by n matrix. So what's the benefit? So I mean, yeah, you do reduce space, but you also reduce time, right? The bottleneck here was computing A transpose A, which we said was nd squared. But now we don't have to compute A transpose A. Basically, A is now pi A. So pi A transpose pi A takes m d squared time. So if m is much less than n, we just replaced an n with an m in the running time. And it turns out we're going to see you can get m to depend only on d. It doesn't have to depend on n at all. So you got a running time at the end of the day, which this n becomes something function of d. So let's just prove this. So first of all, x tilde star is the optimizer for this regression problem, which means that pi a x tilde star minus pi b, I'm going to drop L2 norms, they're all L2 norms, is at most pi a x star minus pi b, right? Because I said x tilde star is the optimal vector for this regression problem. And what is this? This is just pi times ax tilde star minus b. This vector lives in that subspace. It's spanned by b in the columns of A, so it's preserved. Same thing here. This thing lives in the subspace, so it's preserved. That's it. Now you just move this over here. Okay. Questions about that? Yeah. Yeah, so okay, good. So I slightly cheated. I said everything is great because now this n is an m. But I ignored that you have to actually spend time computing pi times a, right? But as we're going to see, you can choose pi to be like the Thorup-Jong sketch. And then pi is like super sparse. So pi a is really fast. So now how do you get the pi's? Good. So you were asking about how do you multiply pi times a? So benefit, bottleneck for computing x tilde star is pi a transpose pi a. And this takes time. Okay, but as you said, what about the time to compute pi a? Well, to answer that, I have to say, what is pi? Okay. Yeah? Is everyone still with us? So let's think about what it means to be a subspace embedding. Let's, so what does it mean to be a subspace embedding? So let me say that, so V is a linear subspace. Let's say the dimension of V is D. So every subspace has a basis. And we can take an orthonormal basis, right? So let's say that U is an n by D matrix. The columns of U form an orthonormal basis for V. Which implies that, for example, U transpose U is the identity. What's the ijth entry of U transpose U? It's the ith column of U dotted with the jth column. So that's only, since it's an orthonormal basis, that's 1 when I equals j, and it's 0 otherwise. Okay, so the definition of being a subspace embedding is that for all v in V, pi v L2 norm squared is 1 plus or minus epsilon v L2 norm squared. But what is v? V is just the set of all vectors ux, where x is in Rd. Right? It's linear combinations of vectors in my orthonormal basis. So this thing is the same as saying for all x in Rd, pi ux is 1 plus or minus epsilon ux. But what is ux L2 norm squared? This is x transpose u transpose ux. And u transpose u is the identity. So this is the same thing as 1 plus or minus epsilon L2 norm squared of x. So what we're saying is that all the singular values of pi u are between 1 minus epsilon and 1 plus epsilon. Or the squared singular values. So that this is the same thing as saying all eigenvalues of pi u transpose pi u are 1 plus or minus epsilon, which is the same thing as saying that the largest eigenvalue in magnitude of pi u transpose pi u minus the identity matrix is less than epsilon. Okay. Questions? This is the operator norm, which means take the largest eigenvalue in absolute value. Take the absolute value of the largest eigenvalue. Right? And if you think about it, pretend that U was not a matrix, but was actually a vector. Pretend D was 1. Okay? If D is 1, what is this thing here? This is just the squared norm of pi U. Okay? Meanwhile, what is this? This is, let's say U has unit norm. This is U transpose U. This is the squared norm of U. So this is the squared norm of pi U. This is the squared norm of U. And if U is a vector, then these are just scalars. And operator norm is the same thing as absolute value. So this is like a generalization of what we just saw, preserving vectors. Instead of preserving vectors, you're preserving orthonormal matrices under operator norm. So you can think about basically doing the same exact proof, right? Do Chebyshev's inequality. The probability that pi u over pi of pi u transpose pi u minus the identity bigger than epsilon is at most the expectation of pi u transpose pi u minus identity squared over epsilon squared. What is this thing? This is the largest eigenvalue squared. The largest eigenvalue squared is definitely at most the sum of each eigenvalue squared, because when you square it, everything's non-negative. So this is at most the expectation of the trace of pi u transpose pi u minus the identity squared over epsilon squared. Right? The trace is the sum of the eigenvalues. The operator norm is the biggest eigenvalue. When you square a symmetric matrix, the eigenvalues just get squared. So this is the sum of the squared eigenvalues. This is the largest eigenvalue squared. So this is definitely bigger than this. Okay? So this is like the matrix analog of what we saw before. And I'm not going to do the computation, but what you can show is that this thing is 1 over epsilon squared times O of d squared over m. So as long as you choose m to be d squared over epsilon squared, you're done. If you use, say, the Thorpe-Zong sketch, this matrix where you have one non-zero per column. Okay? And this thing is due to, so Clarkson Woodruff had they had a more complicated way of doing it that got a slightly worse bound, but they were the first to do it. And then basically this sequence of inequalities I just showed you is from Mahoney and Mang in the same conference, as well as myself and Huiguan. Right. So now, if you use the Thorup-Jong sketch, how long does it take to compute pi a? So pi has one non-zero per column, and zeros everywhere else, and then you have a here. So you can prove that this thing is basically the support size of A. And the reason, right? Oh, question? Okay. Good. Yeah, so let me just say, so what's the reason? Basically, think about A column by column. And for every non-zero entry of A non-zero entry of A means you add the corresponding column of pi to your sketch. But that column only has a single non-zero entry. So you can do that in constant time. So for each non-zero in A, you're spending only constant time to add into pi A. Maybe you can think about that offline. But okay. So there's that. So I showed you this and this. How about point query and dimensionality reduction? Maybe I'll actually switch the order of those. So now I just want to show you basically applications of this pi. Okay, that's what I'm showing you over and over again in different areas. So now I'm doing this one. The idea here is there's this Johnson-Linen-Strauss lemma. It says that for all points x1, let's say for all sets x in Rn, let's say that the size of x is capital N. There exists a matrix, pi, what do you know, where m is O of 1 over epsilon squared log the size of x. Such that for all xy in capital X, pi x minus pi y is 1 plus or minus epsilon x minus y. And as I formulated it where you want to use a linear sketch, it's known that this is optimal, so m being omega, well, let's say the min of n and 1 over epsilon squared log n is necessary. In the sense that there exists a set of vectors capital X that really needs this number, this target dimension. Why did I have to put a min of little n there? Just so we're on the same page.
Well, if m is larger than n, then you can just stick the whole thing in.
Yeah, I mean, I could always take pi to be the identity matrix. Okay, so you're not going to prove that you're never going to prove that you need more than little n dimensions, but we can show that you always need the min of n in this, which is basically the right thing because it says that you should use this until the identity matrix is better. So how do you prove this thing? Design a distribution such that, let's call this D over matrices, just like we design distributions over pies, such that for all x and Rn of unit norm, the probability over pi drawn from this distribution D that pi x, actually let me call it z because I don't want to conflict with that x over there. The probability that pi z minus 1 is bigger than epsilon is at most delta. Suppose you could design such a distribution. Okay, if you could design such a distribution, you would set delta to be 1 over basically n choose 2, where capital N is that capital N. Set z to be some x minus y over the norm of x minus y, where x and y are in this capital X. Great. So what you're telling me is this random matrix pi preserves this vector with high probability, right? So by a union bound, it preserves all of these for all choices of x, y, and capital X with good probability. So you're done. Okay. So what do you think pi should be? Random sign matrix. Okay, so choose D to be uniform over random sign matrices, minus 1 over root m, 1 over root m, m by n matrices, where m is going to be 1 over epsilon squared log 1 over delta. So this log 1 over delta is why you get a log capital N. I still have some time. Okay, and I'm not going to show you the proof. You know, why does this work if you choose m to be like this? But I'll just say it in words. So just now when we looked at the streaming application, what did we do? We did Chebyshev's inequality, right? Maybe I'll just write a little bit. And the idea is, just like in your homework where you analyze the turn-off bound using moments, instead of Chebyshev's inequality, which means the second moment, you take a really big moment. And if you take a big enough moment, you can get the error probability to be delta. So if you go back through your p-set for the turn-off bound, you'll find that if you wanted the right-hand side of your final tail bound to be delta in the turn-off bound, the moment you ended up choosing was like log 1 over delta. Okay, so go back to your solution and look at why that's true. And it's the same thing here. You end up basically just analyzing exactly what I showed you at the beginning of lecture, but instead of taking a second moment, which is Chebyshev's inequality, you take the log 1 over delta moment. Okay, and you could do a computation that's a little hairier than what you did in that p-set problem. There are also like much simpler ways of doing it, but in principle, you know how to do it. Okay. Okay, so that's dimensionality reduction. In the very last minute, that's point query. That's another streaming problem. So again, xi gets updated as xi plus v. This is streaming. And then we have a query fi, now there are many query functions, fi of x should be xi. So people can query what is the ith entry of x. And again, we'll settle for approximation. We won't, yeah, we'll settle for approximation. So we're allowed to output xi plus or minus epsilon times the norm of x. So we're going to use a sketch matrix pi as usual. Suppose we had a pi, again, m by n, such that if you look at pi being pi 1 up to pi n, we have that, first of all, pi I has unit norm. And for all I not equal to j, pi I dotted with pi j is at most epsilon. So our sketch, as usual, sketch of x is pi x. Let's call that y. And we estimate xi as pi y, pi transpose y, ith coordinate, which is pi transpose pi x, ith coordinate. Now notice that, let's call this xi tilde. And notice that xi tilde is just, if you go with this thing here, this is xi plus the sum of j not equal to I of xj pi I dot pi j. Right? In general, pi x is just the sum over j of pi j xj. Right? Whenever you do a matrix times a vector, that's just a linear combination of the columns of that matrix. So this is what that is. But these things are all plus minus epsilon. So this is xi plus or minus epsilon times the L1 norm of x. So the only question is, how do you get such a matrix? How to get such a pi? Apply the JL lemma, Johnson-Linen-Strauss, to x being 0 and then the n standard basis vectors, which implies that the number of rows you need is 1 over epsilon squared log n. Oh, and I should say, where is this from? Right, and the point is, look, as we saw, preserving L2 norms means roughly preserving dot products, right? Because I had this identity. The norm squared of a minus b is the norm squared of a plus the norm squared of b, et cetera. So if you preserve distances between these vectors, it means you're preserving dot products between them. But the dot products between all these vectors is 0. So you're preserving it up to epsilon. That means the new dot products are at most epsilon. That's that. And you're preserving the distances of these vectors to 0, which just means they're norms. Their norms were originally 1. Now their norms are going to be roughly 1. They're going to be 1 plus epsilon or something. But you can normalize them to make them actually 1, and that won't really change this by much. So that's it. Okay. So there are many more ways to use random sign matrices, but that's all I can fit into the time. OK, so yeah, thanks. And please have some baklava.